Good morning, friends. This is Professor Chaubey's physics class. Professor Chaubey, under the heading Physics Made Simple, I am going to discuss today transient currents, in the transient current, charging and discharging of a capacitor. So first I will talk about charging of capacitor. Last time we discussed transient current through RL circuit, means inductance resistance circuit. Today I am giving a circuit, simple circuit, where the E is the battery, S is the switch, R resistance and C capacitor. So RC series circuit. When we press the switch, current starts flowing, charging current, charging condenser. So current flowing is maximum, so maximum current, and then current decreases gradually. Finally the condenser is charged and current becomes nearly zero. Initially there is IR drop here as maximum voltage drop, and when current starts decreasing, voltage across capacitor increases and voltage across resistance decreases. So the total remains E. So that is the charging of capacitor. Current flows in the beginning maximum, and then current decreases. It never reaches zero, but nearly zero, very, very small. When finally become fully charged, and that takes time, too long time, then current becomes nearly zero. So I can write here that the maximum current, charging maximum say, or you can say initial charging current, that is maximum also. What is the current? Charging current, maximum current, that is also maximum. I naught equal to E over R. E is the EMF battery and R is the resistance. That is the maximum current. So at any time, at any instant, I is the current flowing in the circuit. So this I current, you can write here, say I is the current and V is the potential. V is the potential difference, say across capacitor C, this, and Q is the charge on capacitor. Then we can write Q charge, we can write Q is equal to C and V. V is the potential. Or V is equal to Q over C. And we know that current in the circuit is the rate of flow of charge. So current I is rate of flow of charge. That is, we can write that using Kirchhoff voltage law, using Kirchhoff voltage law, we can write the applied EMF E is equal to the capacitor voltage plus I into R, IR drop. That is the voltage across resistance. Well, that you can write now. So this E is equal to V into IR, and what is the I? E is equal to V plus, what is I? I is the rate of flow of charge, that is dq dt, charge per unit time, that is the dq dt, and dq dt is, this I is dq dt means Q equal to CB, so C and dV dt. So we can write here B E is equal to B plus I we can write as C dV dt. So I and then R. So R we can write here C into R. So this is the R we can write say here simply. We have to integrate and solve this differential equation so to get the charging of the capacitor. So we can write say here that E is equal to dV over E minus V, E minus V, and then E minus V in CR dV dt, CR dV dt. So this dV over E minus V, of course we write this side say, or we write say dV over E minus V, say dV over E minus V, and CR dt R over RC. This we write say minus say CR dt over RC. This dV over this dt over CR. So that is minus here. Integrating both sides. Integrating both sides, what we can write? Integrate this, so this and what? So this will be log of say E minus V and on the base E. So that is of course on the base E, log of E minus V is equal to minus T over RC plus a constant, there is a constant of integration, so this is constant. Well, we can get the value of constant K by writing say at T is equal to 0, at T is equal to 0, what we have? V is equal to 0. That is the initial condition. So we can apply this initial condition. T is equal to 0, V is equal to 0. So you can get the value of constant. That will give you the value of K. So that is log E K. Log E is equal to, we put here 0, so log E is remaining here. t is equal to 0, so k. So k is equal to log of E. Yes. So we can write, therefore, you can write this integral log E minus V is equal to minus T over RC plus log of E, that is a constant K. So this you can write, remember that this log is always on the base E. This you can write that log of this, combine this constant here, log E minus V over E. Log E minus V over log E, and this is equal to minus T over RC. So E minus V and E minus V over E, E minus V over E is equal to E to power minus T over RC. This means that E minus V, you can get E minus V is, yeah. So that gives you the value of, say, V is equal to what we are. We are interested in the same. Yes, on that side. So this 1 minus V over E is equal to E minus T over RC, or we can write, say, V over E is equal to 1 minus, or we can write V is equal to how the voltage changes, E 1 minus E over minus T over RC. That is the voltage V of the capacitor increases like this. E is the potential of the battery EMF, and 1 minus E to power minus T over RC. So this gives the growth of voltage, how the voltage changes, and you can write, say, V is equal to Q over C, that is the charge at any time Q, and E is, say, Q naught over C, that is maximum charge. Q naught is maximum charge. So we can write that V, that potential, we can convert into the charge Q over C, capacitance. So in place of this V and E, we can write in terms of Q and Q naught. So this C and C will be cancelled here, and we will get Q is equal to Q naught and 1 minus E to power minus T over R C. So this equation, simply 1 minus E to power minus T over R C. This is a charging equation. Charging equation of capacitor. It gives charge Q at any instant charge, Q charge. So Q is equal to Q naught. Initial, that Q naught is the maximum charge. And 1 minus, so Q naught is the actually maximum charge on the capacitor. So you can see that if T is equal to say infinity here, this becomes E2 minus T over RC is equal to 0 and Q becomes Q naught. So Q becomes Q naught. Charge becomes maximum when time is infinity. Means it takes infinite time to have full maximum charge of the capacitor. So we can get the charging, actually we can plot this also curve just with the time here, and we can just starting from here. So this is Q naught. This is 0, this time. So it takes infinite time in fact. Exponential charging, it takes infinite time to have the maximum charge, Q naught. This is the Q scale, charge increasing like this. And here charge is, say, at the point 0.632 of Q naught. How much Q naught? Or, yeah, 0.632 Q naught, this point. Means Q value is this. So Q will equal this much, Q naught cancel. Then you can say what time here, this time you can put T is equal to RC at T is equal to RC. This becomes e to power minus 1, that is 1 upon E. So 1 minus 1 upon E, you know the value of E 2.7, so put that value, you will get the value 0.63. The Q is equal to 0.632 Q naught. So this time here, this time when this T is equal to RC, at this time the charge becomes 0.632 of the maximum charge Q naught. So this is the exponential charging of a capacitor, and at what time, and remember that we know that TRC, as we have in the LR circuit also, L over R. Here RC is known as time constant. RC is known as time constant of circuit, that is charging circuit. It is because in a time, but R and C is the time unit. So this is the charging for the capacitor, you can say, that is the time constant of the circuit RC. Because E over minus T over RC is the dimensionless quantity. So RC must have the units of time. Only then it will be dimensionless. So this gives us the charging of the constant, and this RC, just we have an RL circuit, so this lambda is equal to RC. Lambda is called RC, time constant. Now, this I have shown to you, that after 1 RC time, this charge becomes 0.632. So this gives us the charging of capacitor, how the capacitor gets charged, what time, how it takes. In RC time it becomes 0.632 of the maximum charge, Q naught. So this gives you the charging of the capacitor Well, now we can see that we can have a circuit, or say we can talk about the discharging of capacitor. Discharging of a capacitor, that the capacitor, how the capacitor gets discharged and how the current. So what we will show, we will make a circuit, say here, this is battery charging. This is the battery, and here we have the resistance R. We have a key here, and then we have a capacitance. C is the capacitance. The same circuit I am drawing, that battery of E connector through R and C, and then this is another key, and this to see the discharging of capacitor. So first of all, this capacitor is charged in this circuit. Say that current flows through the R, and we press the key here. This charging takes place. First part which we have done already, the charging of capacitor takes place here. And then after this is charged, fully charged, what we do? We remove this key and we press this key. So condenser charge, condenser discharges through resistance R. Means first condenser is charged, to the maximum value, and so Q is equal to Q naught 1 minus e to power minus t over RC, this, and then S1 and this switch S2. S1 is first condenser is charged to maximum value, S1 is closed and S2 is open. Now S1 is open and S2 is closed. You open S1 means charging circuit is off, and press the S2 and S2 is closed means condenser is not discharging through resistance R. So discharging of condenser takes place. Now we can write discharging takes place means for this circuit, this equation is, this was for charging, now discharging takes place through this. So now potential is zero. We write the voltage equation, we write Kirchhoff voltage equation for discharging of capacitor. What the discharging takes place? You can see that in this discharging there is no potential source. So EMF is equal to 0. What we have? We can write 0 EMF, and then this is now equal to voltage of the capacitor. We know voltage, and then RC dV dt, that is, this is I. So Ri drop and V as capacitor voltage. So this is the Kirchhoff voltage law, that no potential applied. Zero is equal to potential across capacitor any time, and then Ri drop across resistance here. So this is the discharging equation. Well, discharging equation, now what you do? You can say that you can solve this discharging equation, that how the capacitor discharges through resistance R. So that you can write here that V is equal to RC dV dt, or dV over V, dV over V, this here is equal to dt over RC minus on this side. So this gives us, integrate this, what we get? Log of V on the base E is equal to this minus T over RC plus a constant. Constant is of integration. Well, you can get constant from the initial condition. From the initial conditions, what are initial conditions? Initially at time t is equal to 0, what the voltage of the capacitor, that is the, so we can write t is equal to 0, initially V is equal to the battery voltage E, maximum, at t is equal to 0. So t is equal to 0, V is equal to E here, so you can get the constant value of K. This gives K is equal to log of E, or we can get log of V minus log of E minus T over RC. So log of V on the base E, that is log V upon E, is equal to minus T over RC. Or V over E, or simply B is equal to E exponential T over RC. So we know now V is the, in terms of charge, say Q is equal to CV, that is V potential. So we can write here V is equal to Q over C. So, and there is also Q naught. So that is maximum charge. So Q is equal to Q naught e to power minus T over RC. What does it mean? If T is equal to 0, the starting potential is maximum, charge is maximum, so e to power minus T over RC, T is equal to 0, this thing is equal to Q is equal to Q naught. At T is equal to infinity, e to power minus infinity is 0. So Q becomes 0. So we get discharging of capacitor, that capacitor is being discharged at a time scale. We start say from Q is equal to Q0 maximum at this point say, and then discharge takes place. This is 0. So it is never 0. It is exponentially coming towards 0, and this t is equal to infinity. It means very large. This becomes 0. So this is the discharging. Discharging of capacitor. Transient currents, discharging of capacitor through resistance are the decay is a time constant lambda is RC. You can find out here that 0.368 at Q is equal to, so here T is equal to RC. In the equation, T is equal to RC, e to the power minus 1. So you can get that Q, T is equal to RC. So Q is equal to 0.368 of Q naught. This 0.368 of Q naught. This value. So the discharging of capacitor explains that after one time constant T is equal to RC, the charge of the capacitor becomes 0.368 times of the maximum or initial charge Q naught. So this gives you the discharging of the capacitor through resistance R. And remember, RC is the time constant of the circuit. Time constant is very important for the charging and discharging. That we have this discharging equation, and discharging was 1 minus, like that. So this is very important. So friends, this finishes your charging of capacitor and discharging of capacitor through a combination of R. And I want to take a break here. When we meet next time, just maybe today or maybe next time, we will do some problem of RC circuit. Thank you very much.